So, predicting chemical reactions. First, we need to determine what type of determine what type of reaction is being presented. Write the correct formulas for the products and then balance the equation. So, here we have two ionic compounds that are being mixed together. Since we have two ions for each thing on the left and the right, we can guess that this is probably going to be a double displacement reaction. They're probably going to swap cations. So, doing our swap anions, either way works. So, we can look at this and guess correctly that this is probably a double displacement reaction. So, the anions are going to swap. The chlorine is going to switch over to the hydroxide. The hydroxide is going to attach itself to the calcium. And we're going to get these two products. The last step is balancing the equation. So, whenever you complete the products, note that you're going to have to remember our ionic rules. Hydroxide has a charge of -1. Calcium has 2+, so we need 2 hydroxide when we attach it to the calcium. Aluminum has 3+, chlorine has -1, so we need 3 chlorine with the aluminum to counteract the charges. Then, once you have the equation down, we need to balance it. So, we have 2 chlorine on the left and 3 chlorine on the right. You can initially guess that maybe to counteract this, we need a common denominator 6. So we're going to need to make 3 calcium chloride here and 2 aluminum chloride on the right. That will give us 6 chlorine, or 6 chlorine on the right and 6 chlorine on the left. But now we have 3 calcium, so we're going to triple the calcium hydroxide, giving us 3. And we have 2 aluminum on the right. We'll need to double this, and then we check to make sure everything works. Make sure it's fully balanced. That's the general strategy for balancing. It's just keep adding numbers until it's balanced. So to actually write that completely out. So we have calcium chloride mixed with aluminum hydroxide. We can predict that this is double displacement. So we're going to swap the anions. This would be calcium now with hydroxide plus aluminum, and we're going to swap, and I'll give it chlorine. Next, we need to make sure that these are proper chemicals or compounds. Calcium has 2+, hydroxide is -1, so we need 3 of these. So we have calcium 2+, hydroxide negative. When we combine them, we need 2. We're going to do the crisscross method to get this. And I put 3, that should be 2. Likewise over here, aluminum is 3+, chlorine is negative. So when they combine, you can crisscross the 3, or we just need 3 chlorine for every 1 aluminum. So this gives us a complete equation, but it's unbalanced. So we need to figure out what the coefficients are on the equation, the number in front. One of the methods I like using is count up and do this multiple times. So on the left-hand side, and it's best working with pencil so you can erase. So I have, where are my elements? I have calcium, chlorine, aluminum, oxygen, and hydrogen. How many calcium do I have on the left? I have 1. How many do I have on the right? I have 1. How many chlorine? I have 2 on the left. On the right, I have 3. How many aluminum? I have 1 on the left and 1 on the right. How many oxygens do I have? I have 3 oxygen on the left and 2 oxygen on the right. This 3 on the outside is multiplied inside the parentheses. How many hydrogen? I have 3, and I have 2 on the right. And we need both of these sides to completely match. I usually will start with the most simplest. So calcium and aluminum we don't need to worry about right now. Chlorine is the most simplest. So what least common multiple do they have in common? Be 6. So 2 times 3 gives me 6. 2 times 3 gives me 6. So right now. And then basically I restart. This is why it's good to do this in pencil. So I changed the calcium into 3. And I changed the chlorine on the right to 6. It's the only change I made. On the right hand side, I changed the aluminum to 2 and the chlorine to 6. So now chlorine is the only thing matching up. Well, I know I need 3 calcium, so I would just guess I'm going to come over here and put 3 here and check. So now this has 3 calcium. 3 times 2 will give me 6 oxygen. And 3 times 2 hydrogen gives me 6 here. I know I have 2 aluminum over here, so I'm going to guess that I'm going to get 2 aluminum over here. I have to. So aluminum is now doubled, 1 to 2. 3 times 2 is 6 for the oxygen. 2 times 3 is 6 for the hydrogen. And now these both match on both sides. I have 3 calcium on the left and right. 6 chlorine on the left and right. 2 aluminum on the left and right. And by the way, doing this, you're going to make lots of mistakes. Especially if you miscount. I recommend that when you start working on this, just scratch this out, rewrite the table, as it is very, very easy to make a mistake while counting. But basically, that's basically how you do this, is you're just going to keep adding numbers until you can get the left and right side matching. I will say this. If you screw up on this step, you are going to waste a significant amount of time on this step finding out there's no solution. You need to make sure this step you got down. If you start working on this step and you see there's no way to balance it, that almost guarantees you did not come up with the compound formulas correctly. You need 2 hydroxides per calcium. You need 3 chlorines per aluminum. Some of these problems are extremely hard to balance, and I try to avoid giving them to you. Like, I tried making up ones my first year of teaching, and realized that it took me about an hour to balance, because it was extremely difficult. to figure out because I basically took like glucose and took common formulas. I have learned my lesson since then. So let's try this. Sodium iodide with strontium hydroxide. What type of reaction is this going to be? Double displacement. So what's the formula for sodium iodide? We have sodium. We have I is negative, sodium is plus, so this makes NaI. Strontium. Strontium is Sr, and it's 2 plus. Hydroxide is OH negative. So we need 2 hydroxide for it. And they're going to switch anions or cations. So Na plus Sr. I'm going to put the OH here. I'm going to put the I here. And this is the part what's very, 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 very important. Make sure these are valid compounds. So Na is a plus. OH is a negative. Those charges cancel each other out. NaOH, sodium hydroxide, is a valid compound. I is negative. Strontium is 2 plus. To counteract the charges, I need 2 of these. So make sure you put the 2 down here. This is aqueous. We'll learn about this after a while. This is aqueous. This is aqueous. And this is solid. Now it comes to balancing it out. And this is mostly just the guesswork. Technically, you can use very advanced linear algebra to do it easier. You can make an equation, solve it algebraically, but you'll be working with 4 equations, or equation per element. I don't think y'all's math skills in high school go that far. And the guess method, keep guessing until it works, is oftentimes very sufficient anyway. So we have 1 sodium on the left, 1 sodium on the right. One iodine on the left, 2 iodine on the right. 1 strontium on the left, 1 on the right. How many oxygen do we have? On the left, 2. And 1 on the right. Hydrogen, we have 2. And 1 on the right. So where will y'all begin? So what do you want to do? So I would just realize that iodine is 2 over here, 1 over here. So So let's just go ahead and double that up. So now the sodium becomes 2, and the iodine becomes 2 here. And I would take this one at a time. Realize what I changed. I changed the total number of sodium and iodine. So these two numbers will change. What would be next?
I would say sodium.
Alright. Sodium, we have 2 on the left, 1 on the right, so we need to double it over here. Changing the sodium to 2. I'm adding an additional oxygen, so oxygen will become a 2. And hydrogen will become a 2. Is this balanced? 2, 2, 2, 2, 1, 1, 2, 2, 2, 2. This is balanced. So the other equation is 2NaI aqueous plus SrOH2 plus SrOH2 2NaOH plus SrI2. Just for future context, what do you think this is so useful? And there should be an aqueous here. And that should be an aqueous. And this should be a solid. What do you think this formula is really useful? What does this equation actually tell us? What can we use this equation to do? Because basically, we just guessed at the beginning, right? We guessed that these two will react via double displacement and make this. Why does it go from left to right? What would happen if I mix sodium hydroxide with strontium iodide? Won't it mix together and make this? Why does it go in this direction, not the other? So this is a guess. We didn't really do much information here. Later on we'll learn which way it goes and do it. But what can we use with this? How much sodium iodine is needed to react with strontium hydroxide? Let's say I wanted 5 grams of strontium iodide. How would you make 5 grams of this? Well, I know for every 2 moles of NaI will react with 1 mole of SrOH, strontium hydroxide, and make 2 moles of sodium hydroxide and 1 mole of SrI2. The ratio is 2 to 1, gives you 2 to 1. And we know how to go from moles to grams, right? Remember, mole is just a counting number like dozen. If you had 2 dozen of these with 1 dozen of these, you'll get 2 dozen of these and 1 dozen of that. So if we converted this to grams, we could actually figure out how many grams of this are needed to react with these grams of these to get this. And that's basically where we're going to. Basically, if y'all remember one of y'all's tests, I gave as a bonus problem how many grams of tin was needed to make 10 grams of tin oxide. Tin 4 oxide. So our equation is we have tin, and it's mixing with hydrogen or oxygen. making it'd be O2. So it balances this equation out. Well, it's balanced already. It doesn't tell you how many oxygen, so we assume we have an infinite amount of oxygen. So we have infinite number of grams of oxygen. But we're trying to get 10 grams over here. Well, we know 1 mole of this for 1 mole of that gives us 1 mole of this. So how many moles of this do we have? So 1 mole of SnO2, and you do the molar mass and work it out, and that's basically how you do it. You convert this into moles. That's how many moles of this you need. If this was 0.5 moles, then we need 0.5 mole of this plus 0.5 mole of this gives you 0.5 mole of this. And then we can convert the moles into grams. Alright. What type of reaction occurs between magnesium and copper 2 sulfate? Copper 2 sulfate is a very common lab chemical. In fact, I probably have several gallons of it in the chemistry lab. Yes. This will be single displacement. So what's the equation for magnesium? Mg. And what is it? What state is it in? It'd be solid. It's a metal. It's reacting with, what's the equation for copper 2 sulfate? So copper 2 tells you it's 2 plus. And what's sulfate? So SO4. Sulfur has, we'll give sulfur a +4. Oxygen is always -2. -2 times 4 is -8. So we have, and sulfur is 6. My bad. So 6 plus -8 gives us 2 negative overall charge. So this is a 1-to-1 ratio. So this is CuSO4. And what is this in? What state do you think copper 2 sulfate is? So this is what type, is this covalent or ionic?
Covalent?
Surely not. We did.
Wait. Oh, it's copper.
These are ions.
Oh, ionic. I was just looking at sulfur ion.
So in order to do reactions with ionic compounds, we need to turn them into ions. The most easiest way to do that is to dissolve them in water. Because if we take two solids and put them next to each other, we're not going to get any reaction. We need to make this chemistry easier by turning them into ions. And the most easiest way to do that is to put them in water. So the metals are going to change places. So we're going to have copper left, and this is solid. And then we're going to have in the liquid magnesium sulfate. And make sure we check our charges. So magnesium is 2 plus. Sulfate is 2 negative. That's a 1-to-1, so that's good. So now we need to check to see if it's balanced. So magnesium, we have 1 on the left and 1 on the right. Copper, we have 1 on the left, 1 on the right. Sulfur, 1 on the left, 1 on the right. Oxygen, we have 4 and 4, so that's already balanced. So our equation is magnesium, which is a solid, plus copper sulfate, which will be aqueous because it's being dissolved in water. Then we have copper, which is a solid, plus magnesium sulfate, which is aqueous. So here's a question. I'm going to switch this equation around. And that should be a plus. So copper mixed with magnesium sulfate. What type of reaction is this? Does not react. So how do I know it does not react? How do I know that this was a single displacement and this does not react? Yeah, we mentioned it before when we talked about single displacement. I'll also pass y'all out a sheet. So, active metals have a low electronegativity. They bond with nonmetals more readily because they are less stable by themselves. If a very active metal is competing with a less active metal to bond with a nonmetal or negatively charged polyatomic ion, the more active metal will win. So lithium is the most active. So let's look at this. So we have copper versus magnesium. So we were trying to react. So looking at our equation that we started out with. We're trying to see if copper will replace magnesium or if magnesium will replace copper. So the reason why we know this does not react is we're trying to get copper to replace the magnesium. So remember, the one that's going to bond is the more active of the two. If magnesium is more active, it will not. This will not react. If in this situation. However, if magnesium is more reactive in this situation than copper, it's going to replace the copper. So looking at this, we see magnesium is the 6th most, so it's very active, and copper is way down at the bottom. So this means that magnesium is going to want to go steal that polyatomic ion, while the least active one is going to be left by itself. Does that make sense? And this is where knowing your periodic trends come into effect. As we go left to right, electronegativity increases. And the more active a metal is depends on low electronegativity. Because remember, the metal is wanting to give up its electrons. If it has a high electronegativity, that means it's going to really strongly want it. The lower the electronegativity, the less energy is required to pull that electron off. So lithium is the most active. Actually, the first group is the most active, followed by the second. Most of the first, we see cesium. Where is cesium? It's not even on this. We see lithium, rubidium, calcium. So it kind of zigzags between them. The transition metals are all at the bottom. Most of them are, at least. So if you have a choice between a rare alkaline or alkali metal versus a transition metal, the alkaline earth metal or the alkali metal is going to win versus any transition metal. Your copper and gold, platinum, and mercury, they're at the extreme bottom. Iron somewhere in the middle. So, is this combination possible? It gives the answer. Lead versus magnesium. So, magnesium is stronger than lead. So, that means this will not happen because magnesium is more active than lead. Will potassium replace sodium? Potassium is the third most active element, while sodium is the fifth. So sodium will come over here and replace the sodium. This reaction will occur. For double displacement, the rules are more weird, and we'll get to that later. For single displacement, it is pretty obvious based on this chart. And I believe I do give y'all that on the test. Which ones will? But we also have to know whether or not something is soluble or aqueous. So if something is aqueous, if it dissolves in the liquid. I can't think of a good chemical off the top of my head. But let's look at a double displacement experiment. We have some AB plus CD and A with D plus C with B. This is possible that it only goes this way, usually if one of these is solid. Because what would happen if they both stay aqueous? If everything stays dissolved? Well, that means we could do this backwards. We can go forward and backwards. Some of the time. And we actually see that actually occurring. We see a forward and a back reaction. That are constantly changing back and forth. This is way more complicated than that, but I want to show y'all this experiment. This is by far extremely complicated. It's nothing like a double displacement reaction. It is lots and lots of different reactions. But here's a chemical reaction where you can see it constantly repeating. You can see that based on the pH level, it's either blue or red. It's called the Belousov. I can't even pronounce it. It's very difficult to get working. Indicators and other things, but you see wave patterns of it going back and forth. So, solubility rules and precipitation reactions. Not all ionic compounds dissolve. That's just a general trend. Instead of doing experiments all the time to see which ones will dissolve, we need to know the solubility rules. All nitrates are soluble. If it has a nitrate in it, it will dissolve in water. All ammonium ions, or alkali metals, are soluble. So if it has an ammonium or if it has an alkali metal, it will dissolve in water. All carbonates, phosphates, and hydroxides are not insoluble unless the cation is magnesium, calcium, or barium. So, for example, calcium hydroxide will dissolve, magnesium hydroxide will dissolve, but sodium hydroxide would not. All chlorides, bromides, and iodines are soluble unless mixed with silver, lead, and mercury. All sulfates are soluble except with calcium. What is SR? Just worked on it. Strontium, barium, radon, and lead. That's it. That's 5 rolls. Let's see what.
Sure, the thing I passed out said the same thing.
Yeah, it does. So, is strontium sulfate soluble in water? Which rule tells you? So, all sulfates are soluble unless there's exceptions, and strontium is a exception, so that means it is not soluble. Sodium nitrate. Rule number 1, all nitrates are soluble, so it is soluble. There is no exceptions. Lead chloride. What rule? Number 4 tells you that all chlorides are soluble except with lead. So this is lead chloride, so this follows the exception and would be not soluble. Did everyone see that? Not soluble, soluble, and not soluble. When a solid doesn't dissolve, it is called insoluble. A solid that forms when 2 solutions are mixed is called a precipitate. So, if there is no solid precipitate, the reaction usually doesn't occur. Because we need the reaction to stop. We need it to go from one side to another, and only way that can happen if we no longer produce ions. If it dissolves in water, it actually disassociates and is able to produce ions in the water. So in order for the reaction to work, we also need to have a solid or precipitate on the right side. Usually, there are exceptions to it. So, looking at this, you can tell that this is going to be a double displacement. So, if we look, lead iodide is not soluble. So this is number 4. All iodides are soluble except for lead. So this tells you the reaction will occur. Lead nitrate, all nitrates are soluble, so that's aqueous. Number two, the second one, potassium iodide. That would be problem 4, or step 4, rule 4. All iodides are soluble, and it's not doesn't meet the exceptions, so that would be aqueous. And all nitrates are soluble, so we have a aqueous for potassium nitrate. Because K plus and NO3 remain dissolved, they are called spectator ions and are not included in the net ionic equation. So let me describe what a net ionic equation is. Oftentimes, it gets too tiresome to do this entire reaction. We need this reaction when we need to know if two things will dissolve. If we need to know how much mass, how many milliliters of this do we need to add, how many grams of that do we need to add, we need the full equation. But it's much simpler to figure out a abbreviated form to work with initially, especially if we're going to have like 10 or 20 reactions. So this is the full equation. We can turn this into the ionic equation. The net ionic equation. First step, ignore subscripts and coefficients, and just write out entirely all the ions. We have lead, 2 plus, because nitrate is negative. We have plus nitrate, which is negative. Then we have potassium, which is positive, iodine, which is negative. We'll work on this tomorrow. What I was going to add is we don't do it for the solids. And then we remove everything they have in common.